speaker is Nick, who is a converted mathematical physicist, now doing very kind of abstract computation involving categories and Hopf algebras.
Thanks a lot, and also, thanks to Chris and Ross for the invitation, because I think it's really special that we have this here at the Laboratory for Foundations of Computer Science, because as we heard in the last 3 days in the celebrations, after all, this is a place where people are very close to mathematics, and in a sense also physics, and that they want to find mathematical principles to study programming languages, algorithms, and so forth. And in a way, weirdly enough, my research program is rather well at this, but I'd like to think that it also is a program which has a lot of interactions with other fields. Sometimes it occurs, and sometimes, it's fun, but you decide for yourself. So I came into this group about 2 years ago. I'm a postdoc of Danos and I, who at the moment is mostly in Remarkably in Paris. And when I started I was invited to give a course in quantum mechanics and differential geometry. That's how my life here started for the first 10 weeks. And it was a superb experience because, in the discussions with computer scientists, I would have never thought they would be interested in quantum mechanics. And it was very inspiring. But what struck me was that somehow the questions that were asked indicated that the mathematics used in certain areas of programming languages, which this group is interested in, seems to be quite disjointed from the mathematics quantum mechanics people or physicists in general would use. And in particular, what I'm going to show you today is, at least in a restricted version, a theory of graph rewriting, which is quite common in computer science, maybe not so well known in the physics community, but I'm going to say a bit about it. And what struck me was that I started working in this group to try to find ways to use results from analytical combinatorics, very well-developed field of mathematics, for studying, for example, biochemical reaction networks. And very quickly I realized that this would be a really difficult task because the language of the people who knew graph transformations was completely different from the language I knew as a physicist. Or, I was an experimental physicist for some time, so I used a certain form of stochastics, but that was kind of not of any use in that regard. And why would you even be interested in graph rewriting systems, or as they call it, graph transformation systems? So I should just say that, because there might be many people in the room who have no idea what they're good for, but I'll just say that they are and actually quite competitively, some very good techniques to study a variety of problems. I'm personally, because I'm in the rule-based modeling group, and Danos is the person who invented Kappa, a programming language for studying biochemical networks. That I'm personally most interested in for biochemical reactions, but you could also do sociology, you can study lattice models such as the Ising model, and so on. It's a very universal framework, and you'll see a bit more about it. So, a priori, when one looks at statistical systems, there's a number of communities, of course, who study statistical systems, and there's there's a certain overlap between these fields. But what I'm going to show you is that essentially, what I call the rule algebraic framework, which is today my main result in this research work, it is interestingly a framework which really interpolates, in an honest way, you can use a computation and see what happens, between a number of different mathematical fields. And in particular, I invented this to be able to use ideas from analytical combinatorics in systems of graph rewriting. But I get the graph rewriting systems from actual biochemical problems. So, as you can imagine, this is a slightly ambitious project, and I'm going to show you results. We've managed to get a first paper on this into LFCS 2016, together with Garnier and Danos and I. And some of the stuff will be unpublished work. Okay, so amongst the surprising results of the approach I'm going to show you is that, weirdly enough, I just started out to understand graph rewriting such that I can use mathematics I know, and found 2 new ways of doing graph rewriting. It is also the case that there's a beautiful result, and that is the part I'm going to show you today, because I think it's kind of the best intersection to the audience here. You can re-understand the Heisenberg-Weil algebra, which arguably is a very versatile concept, in this new formalism, and which immediately means that this is kind of a point of entry to then discuss between the different fields. So, and just for the expert who really know algebra writing, simply because of the time constraint, I'm going to focus on the very special case of discrete graph writing, which is good enough though to illustrate the concepts. And I mean, I'm sure I can give another talk somewhere else on the full story. Okay, so, but maybe to get a common point of entry, let's have a quick look. So, and I mean, in the theme of this conference, there is a philosophy pushed forward by Jean Baez and co-workers that there's a description of statistical systems which looks extremely similar to quantum mechanics when you do it in a certain way, and this is called stochastic mechanics. And so basically the aim of this program is to use axioms as far as possible which are similar to those of quantum mechanics, and then of course makes a necessary adjustment to set probability. So the upshot is that, I mean, let's have a look at the Heisenberg-Behr algebra. So this is obviously a very simple algebra, and the way I want to look at it today is from a combinatorial perspective. So the Heisenberg-Behr algebra can be heuristically described as algebra describing the processes of, we have a pool of, let's see if I don't, okay. So we have a pool of indistinguishable particles, and we have two elementary operations. We can either add a particle into the pool, or we can remove a particle from the pool. The slight twist which makes this non-trivial is that we consider the particles in the pool as indistinguishable. So, and this operation of removing a particle, in, if you write it fully, is actually pick at random one of the n particles and then remove it. And what that means is that you have always only one possibility to add a particle to the pool, but you have n possibilities to pick one out. And that is where a certain type of combinatorics comes in. So, when you ask a physicist how would you encode these properties compactly, what you do is essentially you look at the theory of Heisenberg algebra, and particularly in quantum mechanics in particular, the right thing to do is you look at a certain, actually the canonical representation of this algebra on what's called the Sonic Fock space. This Fock space is spanned by basis vectors which are interpreted as pure states with exactly n particles in them. And then you can encode these two heuristic operations in the definition of a representation through action on basis vectors of the two generators of an algebra. And so basically when you act this operator A, which encodes you taking a particle and removing it, the trick here is, and that is where already the non-trivial stuff begins, I just want to mention. So you have to somehow encode, I mean, it's clear what should happen. You remove a particle, you somehow have to end up in the n-1 state. But I mean, what do you do with this prefactor? I mean, after all, you cannot lose information in that representation if you want an honest representation. And the trick in this more stochastical interpretation of the Heisenberg algebra is that, well, I mean, you use a standard formula, maybe from quantum mechanics in the study of the harmonic oscillator. But the interpretation is that this prefactor, I mean, this is a vector and this is a scalar. So you essentially just store this combinatorial factor n as a prefactor. And the trick about it is that if you do, for example, another deletion operation, you will be able, I mean, you lose the information, obviously, I mean, all the particles are indistinguishable. You only know about the absolute numbers. But through these prefactors, you will be able to accumulate, how many possibilities are there to do two deletion events, and so on. And it's fantastic that such, I mean, it's maybe almost too trivial to even mention that, but this interpretation alone can lead a long way to reconstruct chemical reactions from this very simple description. So then there's the other operator, and as I said, I mean, as you would maybe now expect, when you add a particle, there's exactly one way, so you could have written 1 times the n+1 state. But so, and this alone, I mean, if you think about the theory of representations, I mean, one way to specify a representation, or maybe not an elegant one, you have to give the action of all the generators on all the basis states. And once you have specified that, you have, now you can talk about linear applications and so on. But that fully specifies what's called a canonical representation of the Heisenberg-Behr algebra, known as the Sonic Fock space. And I should say, Heisenberg-Behr algebra, it would be, so this is an algebra which can be defined in principle over any field. If it's defined over R, it's usually called the Weil algebra. If it's defined over C, like in quantum mechanics, it would be called the Heisenberg algebra. But And now the question is, if you know algebra theory, there's always the search for the best, most compact possible way to actually encode the algebra. And one standard way to do this is to give a set of generators. First of all, consider the free algebra, where you just have ordered words in the generators with coefficients in the field. And then you have to define the relations that actually, give that particular algebra. So in this case, it's a very simple computation. What you have to do to get to this relation in question, the only one that you have for this algebra, you compute simply how many ways are there to first add a particle and then delete it, versus to first delete a particle and then add one. And when you compute this, you find out, because you do the computation maybe just in this representation, find out independently of the value of n, you get the outcome that is corresponds to the possibility, first add and then delete. And because that is sort of, a bit of representation theory, any representation is homomorphism from the algebra to the endomorphism or vector space. So since this was a statement independent of the value of n, we actually find that also in the algebra there should be a relation that holds, and that is nothing but the canonical commutation relation of Heisenberg. And then the presentation of this algebra would be polynomials in the generator's modulo, which is ideal. Okay. Now, just quickly, so you can, interestingly, now you wonder maybe this was just one type of particles. One can play the game and simply kind of symbolize here like particles of different colors. You can simply take copies of the Heisenberg algebra to symbolize processes in which you have different types of objects. And the logic is, again, like all the particles are indistinguishable, and if you give the specification, take one blue one and two red ones, in a sense, these processes are independent of one another because, when you take a blue one, you have to find a blue one and so on. So it turns out that the multi-species case is a simple generalization where you now have just one copy of Heisenberg algebra for each species. They commute the copies, and the state space is now kind of, in the extreme case, currently infinite-dimensional state space of, possible integer numbers of particles. And the slight twist is that at each possible allowed state, you only have finitely many particles in it. That is, like, even though you can have infinitely many types, a given realization of the system will always have, a pure state will always only have finite many particles in it. That plays an important role because it's, it makes statements a bit more tricky about, like, what are well-defined operators and so on. So, but up to that complication, you get basically the same thing in blue as we say in German. It's like German means something like you almost utilitarian get the same representation. So what should one do with this? So chemists will give you a very complicated theory how to write down a chemical reaction network. One of the philosophies of Dewey and Behr in the 70s was to say, well, if we know what the Heisenberg algebra is, we can, write down the statistical system actually much more compactly. So the idea is you're given a chemical reaction system, it would always look like a certain number of particles of each type on the left-hand side, convert into a certain output species combination of particles at a certain base rate. And now the idea is, so you will basically encode the state of the system as a probability distribution over this multi-species Fock space. These coefficients here will be required to be, of course, like non-zero real numbers, and they should sum to 1. So that would be a state, as you think. It's a slight twist that it's a distribution over, not only counting the infinite dimensional space in numbers, but also in species. But okay. And then there's one very simple equation that governs the dynamics of the stochastic system, and I should say this is like really about the chemical reaction system probability distribution, how it evolves in time. So this equation is called the master equation. If you look at any book on Markov chains, you will have seen that. So the equation says that d by dt of the state is a certain linear operator acting on the state. And now the fun part, that was the first thing when I was studying what even the problem was, how I could attack it. I thought it was quite remarkable that from this to here, this should be just a matter of reading of coefficients. So basically, the operator which implements the dynamics in this Fock formulation is simply, so you basically have terms of the form of base rate, which is the base rate of the reaction, and then make a linear combination of these generation and deletion operators where basically it's like multi-index notation. For example, if you have a reaction A plus B goes to C, then you have the C A dagger minus, and so, I mean, you can read off. Right. I mean, I don't want to spend too much time on this because this is completely standard here. But so the point is that once you have this master equation, and here basically that is why I asked this question earlier. So, I mean, one problem is that even though you can formally write this down, it's not necessarily a well-posed equation. I mean, the equation is relatively well-posed, but we do not know a priori whether there exists a solution, a unique solution, because there's problems with, you know, you can write out chemical reactions that lead to so-called explosive systems. So, I mean, up to the technical modification, if the solution exists, it's known to be of the form e to the th on the input distribution. And now, of course, that is the moment where really the combinatorials amongst us, you know, start listening, because we formulated h in terms of linear combinations of these Fock space, of these algebra elements. Now, e to the th is something which looks like a combinatorial problem to compute that, and we can ask the question: can we compute e to the th independently of the state? Because after all, the chemical reaction system is fixed in this example, and you know. And so it turns out there's some fantastic results. I mean, basically, when you look at the chemical reaction system literature through these goggles, you find that you can, and use results from analytical combinatorics, you find that you can reproduce all the non-analytical solutions for chemical reaction systems with something, you know, called numerical calculus. So, for example, one of the famous examples, which everybody, I think, does chemical reaction has seen at some point, is the so-called Behr reaction system. It's a reaction system where you, in this example, have only one species, and species can, you know, decay at random and be produced at random. And the analytic solution to that reaction system can be written down, and it has a property that, you know, asymptotically it will just converge to a Poissonian. I should say that there's more sophisticated results, and I mean, at least to my knowledge, the best collection of results, most general results, is from Garnier and workers, and it's from 2007. So it's not that, you know, these problems are in any ways, you know, solved in general. Okay, so that was for me personally enough motivation to think, well, this was for chemical reactions. Can I do something similar for graph rewriting? So I should maybe quickly say a word about graph rewriting, because again, this is something was very alien to me as a physicist. So the idea is, when I say graph for the experts, I should say that I mean some very general thing. A graph for me is something like a collection of vertices of different colors, and then any number of edges between them which might be directed or undirected or have roots all in the same picture. Okay, and that is called a graph, and it should be finite. That's kind of the only strict requirement I put on it. And then a graph rewriting rule is essentially an assignment where you take, as an input, a graph, a finite graph, as an output, a finite graph, and then a partial map, which basically tells you which parts of the graph are in the domain and the codomain. Okay. And where it begins is that now, from this very simple idea, you can now formulate graph rewriting. So, a graph rewriting rule, so in this example, I have a rule which wants to find a black and a blue vertex and a directed edge between them. And then the rule would remove that edge, effectively. So, and how does this give a transition system? So the idea is that if you plug in a graph, then you have to find all the embeddings of the left-hand side of this rule into the graph. And for each situation when you do find an embedding, you then apply locally this rule. And the output being, again, the graph. Now, in this case, you have to leave it. And you can imagine what I showed you as Heisenberg was a special case where instead of having edges, I just had vertices. And I mean, my logic was that since I can do chemical reactions for what's now discrete graph rewriting, there must be some mathematics which tells me what is how do I get back Heisenberg algebra from discrete graph rewriting. And I mean, this is an old topic. I mean, I think the first ideas of graph rewriting have been used at least since the 70s, and since the 90s there's some nice theoretical description of graph rewriting for the two main known variants. but none of these descriptions contains any sort of, combinatorial algebraic structure, as would be encoded in the Heidelberg algebra, which was, for me personally, a huge surprise. At first, I just thought this is a communication problem between fields, but turned out not to be the case. So the idea is now, can we find a description of such a graph rewriting system in such a way that we are able to study the combinatorics of the problem independently of the actual transitions that are happening. So as in the previous example, I would like to be able to solve something like e to the th, like an evolution operator, instead of having to act with it on the state, and so we may be trying to solve that. And it turns out that this introduces a beautiful structure into the discussion, which is called the combinatorial Hopf algebra. And I think it would be super amusing to continue this discussion, hopefully in the future, because I have a feeling that this would be maybe a structure that would also be of relevance when you look at quantum systems, which do not have the finite state space. Okay, so let's look at something which I call the rule diagram algebra, which will be the combinatorial device with which we achieve description. And I might have been a bit optimistic about the solution. Is it, I may have had this ambition, so is it readable or? Yeah? Okay. So, simply for reasons of time, and I don't want to take too much of the time, so I will only describe the case of discrete graph rewriting. I will essentially tell you how this formalism reproduces Heidelberg algebra, and we'll say a few words in the end about the results from our Lick's paper, how to do this in general. So the idea is, well, it was quite pictorial, this action, right? It looked like I kind of find, a pattern, and then I somehow transform it. So then a physicist to me came through and said, well, it looks a bit like you want to describe some well-blind pictures, right? So essentially, you attach the pattern. For example, the deletion could be depicted as you have to find a vertex, so there needs to be a vertex, and then its well-blind is terminated. That means from the actual state of the system, it is removed. And the dual operation is that you do not require anything and just produce a new vertex.
There's some edges connected to those graphs.
And that is where then, like if you do the full graph rewriting, then the interesting stuff.
Not just in these pictures, or they're meant to be edges that we can't see.
No, they're not.
No, it's just that at the moment I'm talking about discrete rewriting. And actually these things will encode the algebra, not the graphs.
Those are the word lines. The little edges are the word lines that he was talking about?
I can't see any edges.
That's
why it's about the slides, really. It's not a technical question.
No, maybe I should call it, that's actually the resolution problem. So, so what I wrote on the board should have been, as the resolution is, a picture where you have always on the bottom will be the input, on the top will be the output. In this case, there's no output because you delete the particle. And will be the dA, dagger will be the diagram. What's it shape? Sorry, yeah. I think standing close to it, there's no lights. It's always like when you design and talk on the iPad and the resolution is so good. Yes, but the idea is actually quite simple, although its implementation proved to be nightmare. 9 months to do. Not for this case, but so the idea is that you come up with an operation now. Somehow these pictures should encode transformation steps. And what you need to get to the algebraic descriptions, you need to be able to say what happens when you have many of these steps concatenated. What does it mean to do several steps, one after the other? So there's this very simple idea, and for the Heidelberg algebra, it's not me who came up with this. I will show later a citation from Polish mathematician Paweł Blaszak and co-workers who were the most famous analytical combinatories in Paris at the time. So there's this idea of diagrammatic composition. The idea is essentially that you plug together transformation steps by threading together outputs of one diagram with inputs of another. Much like you guys would probably do a quantum computation, I suppose. Diagrammatic way. only that these are at the moment explicit representatives. So we are kind of going at the moment to the explicit level and looking at individual transformations. So I define an operation which is a diagrammatic composition along what's called a match. And the match will be a 1-1 pairing. In this case, we only have vertices in any event in the input and output. So these are 1-1 threadings of vertices. And now comes the one point which is really key in this whole operation. So in the graph rewriting literature, people tell you how to do one application of a rule along one possible, match. But this will be no good for any algebraic description, because we need to be able to we don't know yet where we would ever apply this transformation. Somehow, if we combine two transformations, we need to store the combinatorial somewhere. And of course, again, the idea comes to the rescue to simply store everything in a vector space. So we'll now have a vector space over these, what I call rule diagrams. And so the composition operation, if it has any chance to be interpretable, must also be of this kind. So basically, you define the composition of two diagrams as a sum of all threadings together in any possible way of the elementary diagrams. And since this is a handy, okay, it's not readable, so I just do it here, just to show the very simplest possible compositions you can do. So here you see already, if I take just the smallest possible diagrams, this one has an input but no output, this one only has an output but no input. So you imagine that the only possible way I can get a non-trivial composition would be in a certain order. So I'm just going to do one example computation. So one of the contributions to this composition is always the composition along the trivial match. So it will be just the superposition. And that has a clear heuristic interpretation. It will be the independent parallel application. So I write this as this joint union. And then in this case, you can, if you act with this on top of this, you can also thread these two together. And so one contribution will be a diagram which looks like this. And I mean, this is already all we can do in this simple example. So the fun thing is that, I mean, this looks almost trivial, right? So, but the fun thing is that from this we can get the Remarkably work of width theorem and other crazy stuff. So, okay. So,
sorry, can I ask this question? So, just to translate my sort of graph rewriting lingo into what you're saying. So what you are calling a match here is what graph rewriting people would call a gluing, right? Because a match means something else in graph transformation.
Well, not with, it turns out in the full formalism that a match to a graph is kind of total action. Yeah, but exactly, it's a word. So now comes already the fun part, because what I didn't say was so far, I mean, this was just kind of the heuristics. Now we have to be a bit more precise. And we need one more ingredient, which is like as for, so a graph, even if we draw explicit representative, in most of the contexts, we always mean the isomorphism parts of this graph. So after all, when we draw a bunch of vertices, the moment we draw them on the paper, technically we have to make them identifiable by their position. What we mean when we do this drawing is obviously that we kind of want to forget this information of position. And the technically correct way to do this is to define isomorphism classes. An isomorphism of a discrete graph being just a relabeling in all possible ways. And in the same manner, we will speak about isomorphism classes of these rule diagrams. And fortunately here it's relatively simple. I mean, whenever we have a superposition of elementary ones, the superposition will be commutative. And we will, I mean, since we have this very simple example of the Heisenberg algebra, we will ever only be able to once match, creator with annihilator. That's the only non-trivial composition we can form. So in a sense, it's completely sufficient to describe any possible element of this particular diagram algebra as a linear combination of diagrams which are superpositions of the creators, annihilators, and this funny composite diagram. And that already is enough to get a first hint of where combinatorics comes in. So now because the superposition is commutative, we can now compute something which, I mean, this is the most general element of this diagram. So now let's ask what happens when we compose two such general elements. And so what you have to do is essentially you, sorry, this is capped by crosses, so this is no longer matchable. So the only thing if you pack one of these on top of another element of the structure is that you can do in all possible ways. I mean, you can always superpose everybody, but the only non-trivial pairs is when you choose to pair some of the outputs of the lower one with some of the inputs of the other. Now, I mean, what I found, I mean, when I first thought this is getting interesting, is because look at the combinatorial prefactors. So this formula basically just says, so if you want to, for example, pair one of the inputs of the top diagram with one of the outputs of the bottom one. So the top one has S1 inputs. The bottom one has R1 outputs. Now the combinatorics is that when you want to choose one of the S1s and one of the R1s, you exactly S1 times R1 possibilities. And that in that particular case should give, yeah, exactly. And that particular gives exactly that S1 times R1 possibilities to form this. And again, superpositions are commutative, so all of the outcomes of the different choices are isomorphic. So you get exactly S1 times R1 this particular pattern where you have one more of these guys. And then you can check that, I mean, simply from pairing bullets, you can get these combinatorial factors, which is quite fantastic, because if you try to do a similar computation in the Heindel method to get, you know, a certain combinatorial formula, it's actually quite tricky to prove that by induction. But here you just look at the graphics and you get these things basically from heuristic of, you know, pairing. So, so what I wanted to show you is, and I mean, obviously, I apologize, this is a very dense topic, and I try to pick like the interesting parts. Maybe at one point I should give longer talk about this in another format, but I at least wanted to show you how this combinatorial Hopf algebra structure plays a role. So the point is that we want to use to the full extent the information that the superposition of this diagram is commutative, because that is the source of combinatorics in this graph we're writing. And then, again, I have only spoken so far about discrete graph we're writing, but okay. So the idea is that, as I said, we start off from candidate for our diagrams, and in this particular case we use Garnier algebra, so we only have very simple candidates. We actually happen to have, in this case, only 3 possible elementary diagrams, so it's maybe an extremely special case, but it's good enough for the purpose of demonstrating this. And then the idea is that the generic element will be a linear combination over the field you choose, R, for example, in these diagrams. And to make this mathematically precise, you say associate to each possible diagram, which needs to be a finite one, but the structure is otherwise not restricted, a basis vector. Then you formally define linear combinations as you would usually do for vectors. And it turns out that when you define, sorry, this should both be D and D. So I call capital curly D the set of all equivalence classes under isomorphism of these diagrams. And I endow this with the structure of an algebra now by defining, sorry, this should be just D itself, by defining a proposition law which simply says if you give me 2 diagrams, D1 tensor D2, I associate to it, you know, their product. And I also define a unit map which assigns to any element of the field times, you know, the basis vector of the empty rule diagram. And it turns out when I do this, then you can check the axioms that this will give an associative unital algebraic non-commutative algebra in the standard way. So I don't have to tell you that. So this is a multiplication, this is a co-unit map, and you can check that these 2 axioms are fulfilled. So next, the more interesting, I mean, that was just, you know, I'm quoting the algebra structure. The more interesting thing is that you almost get almost for free.
Sorry, what was the unit? You went a bit too fast.
Sorry. Okay. So the unit is that you have a base field, K, and you have a map that assigns to each possible, you know, real, for example, whatever field you choose, this real multiplying the vector of the empty rule diagram, which is one possible case of the rule diagram. Yeah, it turns out that in this logic, the empty rule diagram can only be composed in exactly one way as any other along the trivial match. And so that acts as a left and right unit of this composition. I think much as in the talk we have this one, it's a sort of notion of
the blank space.
Yeah, exactly. Okay. So the more interesting thing for combinatorics is this one. So we get, that is why this is called a combinatorial Hopf algebra. Because the co-product has a combinatorial implication. So if you give me one of these, bases, one of the possible equivalence classes of the rule diagram, then I can define a co-product by kind of summing over all possible ways in which I can delete a certain number of the superposition factors from the original diagram and pack them in the other tensor factor and do that in all possible ways, including the way where you don't delete any or delete all of them. And I find that this thing gives a co-product. And I should say again, this part of the story, the way I came up with this connection between combinatorial Hopf algebra and graph writing, because I studied very closely the formalism of Laschka and co-workers who developed this sort of logic for the Heindel algebra and then found how to generalize this to graph writing, which is unfortunately. Anyway, so it turns out that here we have the luxurious situation.
Yeah. Sorry, just maybe you'll say it in a second.
Okay.
Just interrupting in case. Is that the same as summing over all the possible pairs that would compose to the original class?
And that is exactly the complication, because it's not.
Okay.
Because you see that depending on the order in which you decompose this, for example, even if you just decompose, you have a diagram which just consists of one generator and one deleter in superposition. When you decompose that, in particular, you get terms like, one deleter in the one and one. When you then multiply that in the one orientation, this thing would have the one term which is like the non-trivial composition, and the other it wouldn't, which cannot be a true structure because this is commuted. It turns out then, like, in the end effect, this is exactly the computation you have to do. It turns out because...
sorry, this is commutative?
Yes.
Oh, I see. Okay.
But it turns out, your intuition, I think, is right just in a twisted way, because then you have to compute it actually, once. I'll show it in a second. It's a bialgebra structure. Yeah. Anyway, so here we have a luxurious situation that we can actually be very explicit, because we have only like a very restricted type of rule diagrams, the ones with creators, annihilators, and the ones which are not really composed. So you can actually write down explicitly what is the co-product, and amazingly enough, from this diagrammatic reason, you get exactly the co-product you would get in the Heisenberg diagram algebra of Blush writing people. Well, it's not so amazing because when you design it such that amazing myself. Anyway, and now you kind of can define the dual of the unit map. This is a co-unit map where you basically assign to any rule diagram. So if you take one isomorphism class, this co-unit assigns the one of the field if the diagram was an empty diagram. Sorry. It assigns one of the field if it was the empty diagram. If not, it assigns a 0. And lo and behold, it turns out that the set of isomorphism class includes this vector space structure, and this co-unit will give a co-associative co-unit or co-commutative okay. And so again, we can check that these words just mean that these axioms hold, and nobody in this room probably will be surprised by that. And maybe slightly non-trivial, because this has to be very from the bottom up. My construction works from isomorphism class of individual diagrams, and I had to construct a priori. I couldn't know a priori that, I couldn't abstract from that immediately. I first had to check that the axioms hold, specifying it on individual generators, from which I can then deduce that there's this general algebra structure. So unfortunately, I had to go through manually to these computations. So this is just the compatibility conditions which you have to check to prove that actually the whole thing fits in the structure of the Behr algebra. It turned out, even in the general case of graph rewriting, it was a bit nasty, but it was doable. So this will come out hopefully in about a month. So 101 page long paper. Okay. Right, and then comes the step which is like the most abstract of them all. So far we have just checked that somehow composition and decompositions are compatible in a certain way. We then can uplift, like we can kind of jump a step then, because in the theory of Hopf algebras there's one very fortunate special case. If you have a filtered Hopf algebra, and here filtration is just simply by number of components of superposition factors in a given diagram, then standard text and Hopf algebras will tell you that then for those cases there's a recursive definition of what's called an antipode. And I mean, either you know about it or not, don't worry about it. So, but it's just to say that there is a way to get the antipode also, which you need for getting full Hopf algebra structure in a constructive way. And details will be provided.
Next, when you say filters, do you mean graded?
And that is again a weird thing, because one good thing is graded, but it's actually only filtered, because in the moment you compose two elements, you have contributions which might have less than the original number, because for example you can pair two of them together. So it's only kind of a bit weaker than filtered. But it turns out for the purpose of this construction, it is equally good. Yes, it is. Yeah, 1 second. Okay, sorry.
What's connected?
So in this particular case, connected would be this guy, or this guy. So connected in the sense of like if you draw it as a graph, this diagram, it's connected in the standard sense, you would think. So any element of the Rho algebra would be a superposition of numbers of these factors. In that case, the filtration component is just the number of these components. And in general,
what you mean by connected in this world?
yes, yes. Yeah, but unfortunately those details for the general graph rewriting case are a bit involved, so again, that is something for a different talk. That will take a moment. Okay, anyways. Right, and yeah, sorry, I just said it in words. And it turns out that once we do all this, we happily find that this diagram algebra forms a structure of what's called a combinatorial Hopf algebra. And then, I mean, the full paper will also contain. So essentially, this algebra has a fantastic property that the presentation of this diagram is actually, in an explicit way, isomorphic to the universal enveloping algebra over the connected diagrams, which kind of tells us that we have found a very efficient way to describe it. And there's a way to then interpret. So the step to get actual algebra of graph rewriting is then, in this particular simple case, to just compress the diagrams and kind of read out their absolute past and future and worldwide picture, time going from bottom to top, which will tell you these things would reduce to just the empty diagram, and these are actually not transformed at all. And that way you get back to the Heidelberg Behr algebra. And that is kind of what I call the rule algebra, which is in a certain sense a reduction of these diagrammatic composites. So all of this should appear not too far in the future, probably after my next visit to ENS in the archive. And anyways, the story for graph rewriting for DPO case should appear no later than May 2nd, because we went the traditional way and only put on the archive the version which got submitted to links and the accepted version. So, okay. And just to find out, because I think I'm running out of time, so I have already managed to implement some results from Amel calculus and extend some others. So there's a huge mathematical literature on analytic combinatorics, and my main goal of this project is to find, analytical solutions to graph rewriting systems as test cases for algorithms, for example, using techniques from Amel calculus and from this realm of analytic combinatorics. And it turns out there's a beautiful general theory one can develop based on the true algebra. But I've written it up. It's because of the other things are such big papers, it might be only 2 months or so. I can show you the final result. Okay. So conclusion is that in the next paper, once it comes out, and I might send an email around if you are interested, we show that basically, just as I've shown you how chemical reactions can directly be encoded once you know Poissonic Fock spaces, you can encode graph rewriting systems directly in this algebraic framework. So basically the representation of this root algebra will be a sort of, the graph version of Fock space. And amazingly enough, stochastic mechanics, so the full formulation of probabilistic theory, is mutant-simultaneously exactly the same as in the case of chemical reactions. So all the formulas, you find analogs of all the formulas, and that's what we call the stochastic mechanics of graph writing. So in a sense, this establishes the first bridgehead between a lot of different communities, because it turns out that a physicist who looks at this now will just think, oh, okay, this is just a different writing system. The graph writing person can now ask questions to physicists about which formulas are of interest, and formulas such as the ENS theorem telling you about evolution of observables. And there's many nice formulas you can get from the possibility to study the algebra independently of its representation, which in physics was a success story of all these combinatorial results, also in quantum information, and so on. But the main work, and I just the project, it basically just started in the last 2 weeks for real. So I'm working with Vincent Danos, with Jean Crédin and Jérôme Ferré, who are the some of the main contributors to this programming language, Hopf. And I found a way to encode this language in this new rule algebraic formulation. And we are currently trying to exploit this formulation to not only maybe find analytic examples, but more importantly, to streamline some of the algorithms and maybe come up with new ideas for algorithms. Because I should maybe say Kappa is very important because it's at the moment one of the few chances, there's other ways to do it, but I mean it's a good chance with Kappa that you might be able to describe biological organisms as a whole cell model. It's a very powerful language. So any small improvement even in the algorithms could be of great practical use, which is why I'm in this group working mostly on it. But there's also encoded the game theory and network theory, which we are exploring. So I hope to be keeping in touch with you guys, maybe in one of the next meetings, and show some of the applications. And with that, I would like to thank you all.
If you can answer it quickly. So early on you showed that the equation operator is sort of crucial to formulating the chemical reaction. Now, can you give any intuition what the corresponding operators would be in a graph case? Because in the discrete case it's clear that you can sort of remove something and add something, but not much more.
Yeah. So it turns out that for this umbral calculus I was talking about, there's an interesting algebra which I would call the graphical Heisenberg algebra, where you basically have, so essentially these diagrams now will be extended to cases where the inputs and outputs are graphs, and now you can have special cases where you kill a complete graph or create a complete graph. And indeed you're rewriting these things from something which looks much like the Heisenberg algebra, although of a very infinite type of humans. And they have very important applications because, after all, in a very crazy way, you can describe a graph writing system on a finite state by replacing the full graph with its image. I mean, it's obviously not a good way to encode it, but it gives kind of an outer hull for all possible applications of graphs, graph writing rules. It's a good tool for algebras. So, yeah.
Can you briefly give us an idea of what changes when you pass from discrete to continuous setting?
Sorry, what do you mean by continuous? I meant this on graphs versus connected graphs. Yeah, okay. So the interesting thing is when you try to reproduce this logic with having graphs, that there's one topological constraint, is that an edge must have its endpoint, right? So the new idea is that when you can compose, for example, you could just start from having, for example, an edge and just keeping it. If you match that, it will count the number of edges. If you now cross-compose it with the vertex deletion, for example, that is a perfectly well-formed expression. But when you now reduce this thing, you are kind of losing the endpoint. So there must be a way how you deal with these sort of errors, and it turns out it's exactly how you deal with these sort of faults, that you get 4 types of graph rewriting. So it's a bit of an involved story, but it's actually not that complicated, surprisingly.
Just about this, basically, it's a very quick question. If you want to extend it to arbitrary graphs, you will have to take these isomorphism classes of arbitrary graphs. Now, the problem of finding isomorphism classes of graphs and subgraphs is known to be quite hard.
Exactly.
So, how do you foresee that will impact on the practical applications of this term?
So the trick is exactly that since we have now an algebra with which we can independently study compositions of the rules, which are typically quite small versus the graphs, which in real life application are like 10 to the 6 or something, is that we can devise algorithms that use it, for example, can compose 10 steps of the system as a collection of rule diagrams. And it actually turns out that since the isomorphism are compatible with the algebra structure, that we can even afford to first compose and reduce and so on without checking isomorphism. And only after 10 steps, for example, checking isomorphism on these first on the rule diagrams themselves, that is relatively cheap. And only then when we apply that, we have to, work with the standard isochecking. So we basically gain that we can lift the problem in several steps before we have to work with isochecking. And there's other implementations we can do which have to do with expectation value of graph counting intervals. We actually never have to deal with that problem until, except for the rules themselves. So in practical application, it is a tricky business to find good applications of this.
So you're saying that as long as you deal with the isomorphism problem in the rules, you can prove a result that says that as long as you take isomorphic graphs.
Yes, so that's actually one of the things in the big paper. Yes. Okay.
Thank you.
Okay, thanks for using that. Thanks.